I did a little bit of background here to remind ourselves of where we've been since it's been a bit of an eventful last couple of days. So first thing is, can you guys see the PowerPoint slide? You should currently be able to see definition, relation in green at the top. I see a couple of yeses. Awesome, it worked. I am currently on 2 monitors, so I am attempting to share only 1 monitor so you can see everything you need to. All right, so to remind ourselves, we've been talking about relations for a little bit before now, and our relation was defined as pick your favorite letter for the name of the relation. I defaulted to R because I was super duper lazy, and it's some subset of A cross B. So remember, that's just a bunch of ordered pairs where the first position of the ordered pair, if you're thinking in terms of XY coordinates, the X coordinate would be from A, the Y coordinate would be from set B, and we will most frequently be talking about some relation, and we just say on set A, that would be a subset of A cross A. I don't think I wrote down that second part last time. Now, one of the things that we ended on last time was talking about paths. So here's the formal definition of a path. So our path here is, first of all, you have to have some sort of relation, and then you're looking at just a list of a bunch of elements from your set. Notice we can't have the 2 sets of the A cross B. You've got to have the 1 set so you actually get all these guys. And to find the consecutive elements in that list, notice consecutive elements have to be related to each other. Now, last time we talked about digraphs, so if we did this in terms of a digraph, you'd start off and you'd have your element A, you'd have some arrow to your element x1, you'd have some arrow to your element x2, and you keep continuing until you get to the very last guy you ended at B. And technically last time we didn't worry about if we use the same vertex more than once or not, if we went over the same arrow more than once. Technically speaking, this guy is in graph theory called a walk as opposed to a path. However, I'm not going to get that specific. I'm just going to keep it in terms of path because that's easiest. And just as a heads up to note, standard format for your relation, this guy is going to look like R equals, and then you've got some elements, maybe A, comma, B, and then more of them as you go on. Okay? So just to remind ourselves of that. So that's where we've been. Now, I'm not going to focus overly much on the digraphs. Actually, I shouldn't say that. We'll use pictures as needed. So next thing that we talked about last time, or I should say next time, that we ended right before we got to is something called a cycle. So a cycle is simply a path. Technically, I'm not going to get into the technique. A cycle is simply a path where you start and stop at the same place. So in terms of an example, maybe you started at A, maybe you went out to your x1, maybe you went down to your x2, and then you came back to A. So that would be a cycle. Technically, there's 2 things, one called a cycle, one called a circuit. A circuit looks just like what I drew, where you can't repeat anything. A cycle is where it's okay to start repeating things, okay? Normally, it's common to go ahead and as soon as you get back to A the first time, that's when your cycle is going to terminate. But a cycle could look like this in terms of crossing each other where you actually have a vertex right there. Where a circuit, that's not allowed. Again, we're not going to go into that theory for us. We're only going to say start and stop at the same place. Got myself a little sidetracked there. Sorry about that. We actually talked about a relation, Rn, last time, but we didn't do the naming convention. So this guy here is you start with some given relation. Rn is a new relation that you build, and it's all the guys that are length n paths from your original relation. So notice here the ordered pairs that are in your relation Rn. This is where your length n path started, and that y is where your length n path stopped. And that's it. That's all Rn is. Now, you can do tons of things with Rn. We're not going to. We're only going to focus on one of them, and this is the one that we actually, the example we ended on last time. This is the relation R2. So notice the 2 in the exponent. That corresponds to your n. So this is a new relation built from an original relation R. and it's your set of all your ordered pairs where you've got a length 2 path that starts at X and ends at Y. And we did a little technically called a decision tree to go and find all of those ordered pairs last time. So that's where we've been. Questions so far? Kind of okay so far. All right, seeing no questions come up, I'm going to go ahead and jump now into the next thing, which should be an example. Nope, it wasn't. It was a comment and homework, so just a second. First of all, your homework's probably going to get changed after how far we get to in the math material today, but some background. So these are 4 things that I'm not planning on really going over a lot in class or in this virtual class that we're having, and that's because we already know about them. So the only new thing is the second one, R, that looks like a -1 up top. But these 3 guys, the complement of R and then R, the union of R and S, and the intersection of R and S, remember, your relation is just a type of set. So if you want the complement of your relation, that is simply whatever cross product it's built from, and then get rid of all of the ordered pairs in R. That's literally it. So here your universal set is that cross product. If you've got your R is built from set A and only set A, it would be A cross A, subtract out all of the ordered pairs in your relation R. Now, any guesses what you would do for either the union or the intersection? And since your mics are muted, you'll need to respond to that if you got an idea via the chat. Don't overthink it. Anybody got a guess of how you compute R union S or R intersect S? Yep. So this would be exactly the same as any sets. So what do? With the union, just dump all your ordered pairs together, cross off any duplicates, and for intersection, find all of the ordered pairs that are in both of the 2 sets, or relations as sets. Now, here's the part that's different. Okay? So, for our inverse, we have to do a little bit of background, and the little bit of background is talk about what R is. So I'm just going to do an example here. So maybe you have 1, 2, maybe you have 2, 2, maybe you have, I don't know, 3, 1. I'm going to be super lazy. And suppose this relation is on the building set, and I'm just going to write down one of them again because I'm super lazy, of building set 1, 2, 3. This guy is actually a function. Anyway, we don't need that yet. So our inverse in this section, the inverse is simply you take each ordered pair and you flip-flop or you swap their elements. So for the first one of 1, 2, when you swap the order of the ordered pair, you'll get 2, 1. When you take the middle one, 2, 2, when you swap it, well, nothing changes. And the last ordered pair there of 3, 1, when you swap its ordered pair, you'll get 1, 3. Now, I'm not going to lie, it fundamentally bothers me if those ordered pairs aren't in some sort of systematic order, but the sets order doesn't matter. To address the last question, the A cross B and then slash R, slash in the way that you typed it actually means something else, but it's set subtraction. So let me write that down. Set subtraction. And remember, set subtraction was where you remove any elements of R that are inside of the A cross B. All right, so that's a comment in terms of homework. The R inverse was really the main one that I wanted to go ahead and let you guys know about. So everything else today, which won't be too much, I'm going to be talking about properties of sets. I take that back. I had one example. So let's do this one example. I forgot about him. So if we wanted to find a cycle inside of this digraph, suppose you want to find a cycle of length. Oh, let's do length 2 first since that's in order. Anybody spot a cycle of length 2? And I'll prep up for the other 2 as well. There aren't as many options in this digraph as in other places. Ooh, be careful, guys. Cycle. What's the key thing? With a cycle, it needs to start and stop at the, what? The same point. Oh, you sneaky person. Yes, that is a length 2 cycle. So the sneaky one that somebody wrote down was 4, 4, 4. And yes, there's also 2, 3, 2. Pretend that 2 looks less like a weird scribble and an L. There's also 3, 2, 3. The main thing is you want to start and stop at the same place. And if you write it out in this formatting right here, notice the number of arrows corresponds to your length. I really like the arrows myself. Now, what if you wanted to find a length 3 cycle? Anybody spot one? Yes, there is that one. So technically speaking, you could just keep looping at 4. And that's the other one. So there's also the cycle that goes here. And you can start and stop at either 1, 2, or 3. It doesn't matter which one. The only thing you got to remember about cycles is you want to start and stop at the same location. So here, if we grab one of these guys, if it was me, I'd probably be super duper lazy and say 1, 2, 3, go back to 1. Okay. Now, here's the sort of trick question for perhaps some of you, but definitely not one of you. Can anybody find a length 1 cycle? Yes. So if you guys hadn't already told me about the all 4s cycles previously, this one can be really hard for people to find. But yes, the only way you're going to get a length 1 cycle is with a loop. And everything you guys have been sending have all been paths, but not all of them have been cycles. Watch out, the difference in our class between a path and a cycle is a cycle first and last vertex or element from your set is the same. A path would be if they're different. So, and that's it for this example. Any questions before we move on, or okay with this guy? All right. So next thing is the properties of relations. There are 6 properties of relation, and based on time, I am hopeful we'll get through some of them. Definitely we'll get through some of them. So the first property is that there's actually 2 properties that are highly, they typically go together. The first one is the reflexive property. The reflexive property says, hey, you've got some relation, it's on some building set A. This relation is called reflexive or has the reflexive property if for every element in your building set A is related to itself. Now, structurally, what does this mean? So if you're actually in your relation, so you're in your ordered pairs, what this means is you've got every single ordered pair where the first and the second coordinate are exactly the same, and this is true for all of your elements in A. In other words, you got all of your doubles. I realize that doubles are not in any way, shape, or form sorry. Yes would be the answer to that last question that about the length 4 cycle. You could do that. If you ever go and work into graph theory proper, there's some extra things where you can't repeat edges, you can't repeat vertices, and you are starting to get into some of these guys. But if we haven't been talking about any of those restrictions, yes, you've got exactly 1, 2, 3, 4 little arrows. You're starting and stopping at 2, and you're following those arrows on the actual picture of the relation. You're good to go. So speaking of digraphs, what would it mean for a relation to be reflexive in its digraph? Or what would you see in its digraph, I guess I should say. So in the digraph, what you would see is on every vertex, you would have a loop. And that's literally it. So you would have Oh, no, don't do that. So you would have all of your loops. And then the last thing that we've done in terms of relations is we've looked at the matrix of the relation. If you're coming from the relation, it's called a matrix of the relation. If it's coming from the digraph, it's actually called an adjacency matrix or an incidence matrix, depending on what you need to encode. And I realize that was super vague. You guys don't actually need that information. So if we're looking properly at the matrix associated with the relation, what happens if everybody's related to themselves? That means along the diagonal of your matrix, you are going to have all ones. So those were trying to be all ones. I realized the last one didn't work. I'm being very careful not to have my hand touch the touch screen right now because of that weird sizing issue just a second ago. Okay? And that's it for the reflexive property. We'll have an example in just a second, but let's go to the property that goes hand in hand with the reflexive property, which is the irreflexive property. Be careful. These two properties feel like opposites of each other, but it's not a binary choice, and we'll see that in an example in just a second. So the irreflexive property, that suffix of IR is telling you that it's not reflexive, but it's more than that. So you got some relation. It's called irreflexive if you pick any element in your building set and it's never related to itself. So if you're in the actual relation, you're not going to have any of those doubled up ordered pairs. You will never have your A, comma, A in the relation for any of your A's in your building set. In the digraph, any guesses what would happen in the digraph? And I'll prep up the matrix while if anybody's got a guess, feel free to use that chat. Any guesses what would happen in the digraph? So maybe I should rephrase that. Do you think we could have a loop in the digraph? Feel free to chat or try. There's some answers. Yep. So irreflexive means you can't have a loop, and it's not just for one vertex. It's no loops, period. Okay? So none of our vertices, none of our elements would ever have a loop if you draw the picture of the digraph. Now on the matrix, if A is never related to itself along that diagonal, you're going to have all zeros. And I can't remember if I said this in class Thursday or not, but if you've never played around with matrices before, we'll talk about what we need in class, but if you want to look up extra information, I've gone ahead and posted extra information on matrices that you can reference as well. So that's the properties of reflexive and irreflexive. We're about to jump into examples, but before I go to the next screen, has everybody got what they needed or wanted to copy down so far? All right, seeing nobody shout, I'm going to go forward. So suppose you have the following example. Suppose you've got a building set A of just the integers 1 through 4 because I'm super lazy, and went ahead and pulled the relation from that cross product of A cross B to be 1, 1, 1, 3, 2, 2, 2, 3, 3, 1, 3, 2, 3, 3, and 4, 4. What do you guys think? Is this relation reflexive, irreflexive, none of the above? Any guesses? So I got a couple of you guys starting to give answers here of reflexive. So how would you determine if it's reflexive? The key thing is who's your building set. Our building set says we have a 1, so we need to have the ordered pair 1, 1. We have a 2 in the building set, so we need to have the ordered pair 2, 2. We have a 3 in the building set, so we need the ordered pair 3, 3. And that last guy in the building set 4, we need to have the ordered pair 4, 4. So yep, this guy is totally reflexive. And if you wanted to say a reason, you'd say because A, that was trying to be an A, comma A, is inside of a relation for all A's in our building set. And that just says, yep, we actually checked them all. Okay? And that's it. Now, what happens if we had a different example? So this guy is still on the same building set 1 through 4, but now it's defined not by way of all the ordered pairs, although technically it is a set of ordered pairs, but now we're defined by way of set builder notation. So this one says we're going to go ahead and have ordered pairs. I went ahead and distinguished them as two different characters, A and B, where the criteria is that the first coordinate or the first position has to be less than the second position. Now we had an example very similar to this previously, and what did we say? We said if we wanted to have an ordered pair that started with 1, we could have 1, 2, we could have 1, 3, we could have 1, 4, all of those are fine. We started the first position with a 2, we could have 2, 3, we could have 2, 4, and if we started with a 3, we could have 3, 4, and we can't start with a 4 because there's no number in that building set A that's bigger than 4. Okay? Now, even without writing out those ordered pairs, could we have determined if this particular example of a relation was reflexive or irreflexive? What do you guys think? Can we figure out if this guy is reflexive or irreflexive? I see a couple of you giving answers here saying irreflexive. Yep, this one is totally irreflexive. And what's the key thing there? We don't have any of those ordered pairs that are the same. And I'm going to claim you can actually see it from right there. Why? That inequality tells you that A and B are never equal. And if they're never equal, that means you can never have that doubled up, that ordered pair of 1, 1. So in these two examples, just looked at the individual ordered pairs, and quite honestly, with reflexive and irreflexive, it's often really easy just to grab all of that information out of the ordered pairs, but you can totally do the same thing in the digraph. The digraph, you'd either look for all loops or no loops on the picture, and in the matrix, you'd look for either all zeros or no zeros on the diagonal. Questions about reflexive and irreflexive? There's really nothing more with those two properties. Okay, seeing nothing come in from you guys, I'm going to go ahead and jump to the next slide, which is our next properties. So the question of the randomly created sets, yeah, kind of. I created them on purpose to grab certain properties, but in terms of, yeah, they were pretty much just designed to be examples for the course. They were only designed to grab certain properties. Like for those two examples, I wanted to make sure one that was reflexive, one that was irreflexive, and that was really it. And to have them somewhat small for you guys. For the next properties, there's 3 of these properties that are highly similar. Well, they're not really similar, but they have a tendency to be grouped together. The first one is the symmetric property. The symmetric property is somebody that is extraordinarily important that we'll see in the future quite a bit. Yes, so the answer about for reflexive, we don't have to have every ordered pair. So in a relation, you don't have to have every possible ordered pair. You just pick some of them to then have the reflexive property. You just need all of the ordered pairs where both the first and the second position are exactly the same for every number or letter or character that you're using. Yes, that's the key thing with reflexive. All right, so for symmetric, you're going to be symmetric if the following happens. And this one here is different from reflexive and irreflexive. Reflexive is all the ordered pairs or all the loops. Irreflexive is none of the ordered pairs or none of the loops. They're the two extremes, all or nothing. Symmetric is not like that. Symmetric has an if. Remember what an if says. It means you're looking to see if this happens or when this happens. So if you know that somebody A is related to B, in other words, you've got, so in the actual relation itself, if you have some ordered pair AB in your relation, then automatically B has to be related to A. So that means you'll be able to find the reverse of that ordered pair in your relation too. Notice, again, you don't have to have all ordered pairs, but for every ordered pair you do have, swap the ordered pair, and you'll be able to find that second ordered pair in your relation as well. Note what this means. This means in terms of sets, if you take the inverse of your set, of your relation, it should be exactly the same as the original relation, is what that means in terms of properties as well. Now, in terms of the digraph, what would this mean? Well, if you have A and A is related to B, well, that would mean automatically you have to have B related to A. In other words, anytime you have a connection between two different vertices in the digraph, you have to have a two-way street, if you will. You've got to have arrows going both directions. Loops, totally fine. Not loops, totally fine. Reflexive, symmetric, or symmetric and irreflexive are what is known as independent, meaning you don't get one for free if you already have the other one. So it would be so loops or not loops, no worries here. It doesn't matter which way or the other. And then the last thing is in terms of matrices. If you've never played with matrices before, this probably isn't something you need to worry about. If you have played with matrices before, I'm going to get a little bit technical. What would happen with symmetric? If you look at the diagonal, you don't care what happens on the diagonal. 1s, 0s, combos, doesn't matter. But positionally speaking, suppose you go 3 positions over right here on the first row. Then on the first column, 3 positions down also has to be a 1. In other words, if you folded this matrix along the diagonal right there, all of your 1s and 0s are going to match. The technical term is you have a symmetric matrix, which is the transpose of the matrix equals the original matrix, and we didn't use that terminology. We did M. The transpose of M equals the original matrix. If you don't know what a transpose is, don't worry about it. If you're not comfortable with matrices, again, don't worry about it. In our class, you will always be able to take your matrix and translate it into either the ordered pairs or the digraph. Okay. And here's hoping I wrote small enough for the next fly-in. Barely. So the next property that we have is something called asymmetric. So asymmetric is if you have A related to B, this implies, oh no, the lesson didn't fly in. So that came out in back. All right, so we'll back that up. I'll just put it in. This implies that B is not related to A, and you never have any loops whatsoever. Okay? So the slashes are going to come in a second. I just didn't have them timed in correctly. What this means in terms of your relation, I'm just going to stack it in the same column as above. If you've got A related to B, or the ordered pair AB is in the relation, this means if you reverse it, B comma A is never going to be in your relation. In terms of the digraph, between any two different vertices, you'll have at most one connection, so only one-way streets, and you will never have loops. Well, that accidentally came in. We'll just deal with it. And in terms of matrices, if you look at positionally the same thing, so here the 1, in whatever position that is, go to the corresponding position if you fold it over the dotted line, this one would have to be a 0. So when you look at those corresponding positions in symmetric matrices, they have to be the same, either a 1 or a 0. In the asymmetric matrices, one has to be a 1 and one has to be a 0. And along this dotted line, this is where you have all and only zeros. And let's go ahead and finish with the anti-symmetric. In terms of in the future, the ones that we're going to need the most are symmetric and anti-symmetric. So anti-symmetric is totally almost asymmetric. So what it is it's got the same criteria. You're wow, I didn't spell that right. So you are anti-symmetric if A is related to B, implies that B is not related to A. So this gives you the same thing as the asymmetric as above. So this part's the same. In terms of the digraph, you still have, if A is related to B, you only have that one direction. But now loops are okay. That really is the big difference. And we said loops, that's a P. And for the matrix looks exactly the same, except along that diagonal line, it's okay to have not zeros. So 1, 0, anything's okay. Huh? So that's the next properties. We'll end on an example of a question that goes over all of these guys. So any questions before we look at this in an example? I think I have this example prepped up on Poll Everywhere, so we'll see if it pulls up. All right, so moving to the next page. This should right now be initialized. Yep. If you go to this, our standard Poll Everywhere place, so what we've got here is somebody that looks very similar to the relations we've seen in the past. And while I'm talking, I'm assuming that you guys can go find this either on a computer or through a phone. We've got our building set 1 through 4. Our relation is the ordered pairs 1, 1, 1, 2, 2, 1, 2, 2, 3, 1, 3, 3, 3, 4, 4, 3, and 4, 4. And we want to know, is this guy reflexive, irreflexive, symmetric, asymmetric, and or anti-symmetric? And if I put the settings correctly, you should be able to select as many as are correct. Yes, you will totally see a weird yellowy thing if something comes in front of my screen. Are you both only seeing a yellow screen right now? Okay. Just a second. I want to keep those guys. Just a second. All right. Can you see the desktop now? Excellent. So sorry about that. It looks like when we jump to Poll Everywhere, it's having an issue. So I guess that makes my life easier in the future. I don't have to type PowerPoints if I don't want to. See if you can't answer this guy through Poll Everywhere. Sorry that it's only got one thing initiated. Hopefully there's only one answer. Yes, the URL is the same. Here, let me type it and send it in the chat to everybody. I don't want to change out what I'm sharing with you guys and have everything change on you since we only have like 30 seconds left of class type thing. It is polleverywhere.com/birdsong. If you're going to the URL, if you have the app already installed, look for the birdsong. Sorry about that, guys. I'll try to get that working a little bit smoother in the future. So these are properties. These are not types of relations. You can actually talk about types of relations, and we'll get into that next time. But these are simply properties that relations have, and when you switch to types of relations, that'll be if I have, say, the reflexive and the symmetric property, then I'm blank type of relation. Yes, a relation can have multiple properties, which is why I'm regretting not letting you guys have multiple choices. Apparently, it is a single multiple choice question instead of a multi-answer allowed. And what we'll see with our examples next time is examples where they have almost all of these properties. But since we are totally at the end of time, are you guys okay if I show you guys what the answer is here? I've only got 40 of you responding so far. It's not everybody. The rest of you want to give me a guess real quick? It's okay if it's wrong. I'm not going to score this off of right or wrong. I'm just going to help to see who was here. That way, if you weren't here, I can go in and contact you guys. Okay. I don't see any more people adding responses, even though there's supposedly 10 more of you here. So here are your responses. The overwhelming majority of you have totally said, oh, you can't see this. Ugh, let's try this. Okay. We're not going to do that. So I just pulled the responses, which you guys can't see because it's not working through PowerPoint. The overwhelming majority of you guys said that this was had the reflexive property. Yes, you are totally right. The reflexive property works here. Okay? Now, if you have the reflexive property and you're not the empty set, what does that mean about the irreflexive property? It's not going to happen. Okay? Oh, you can? Awesome. Excellent. That does explain why so many of you went now to the choice A. In terms of the symmetric property, you've got some good thoughts in terms of it coming, of a possibility of being a symmetric property until we get here to 3, 1. Do we have any ordered pair that's 1, 3? And everybody, or at least the people who've contacted me or to all the class, have said, no, that's correct, which means you're not symmetric. Now, here's something to know about asymmetry. Asymmetry, you can't have any loops. With these ordered pairs, do we have any ordered pair that would correspond to a loop? Loop on a specific vertex. So yes, you're right, we definitely do have some loops, but if you're looking at specifically a loop on one vertex, maybe you go ahead and grab that very first one, so that means you can't be asymmetric. Yes, this is true, you have multiple loops. Oh yes, in this case, because it's reflexive, you can't be asymmetric at all. So that's a quick check. And the last one is anti-symmetric. Anti-symmetric doesn't matter about loops, but what you can't have with anti-symmetric is you can't have these doubled up pairs, the in two ways. So the 1, 2 and the 2, 1, you can't have both of them. That would correspond to a two-way street on the graph. So you can't have anti-symmetric, and that's probably why I didn't check to allow you guys to have multiple